voltage division. So this episode is a really important one. This is, and I feel like I say this every video, but this is the most important thing yet. I mean, everything just builds and builds and builds, but I still consider this to be completely fundamental. This is so baseline, so important, and so this will pass on. This baseline knowledge will grow into everything else that you use in electrical engineering. This is so powerful and ubiquitous. You absolutely must learn this, master this, understand this, etc., etc. So I'm going to go ahead and draw an example circuit of what a voltage divider is, and then I'm going to talk about it and symbolically derive how to describe it. And so hopefully you can follow along with me. So give me just 1 second. It's funny. I mean, this is something that it almost proves my point just how important this circuit is, because we've actually already worked with it. We just haven't thought about it in this way that I'm about to talk about yet. So what do I mean? Well, okay, we have a source voltage and a current with two series resistors here, R1 and R2. So there's a source voltage and this current flows through both. They share the current because they're in series, right? And also, based on the resistance, there will be a resultant voltage across each resistor, V1 and V2. Now, based on the techniques and principles that we've already taught and talked about, we all know that if I gave you information about the source, whether it be the voltage or the current, you could go in and do some circuit analysis and tell me, oh, what's V2? Or you could tell me, oh, what's V1? You could tell me the total current flowing through this circuit. If I told you the voltage was 12 volts and I gave you each of the resistances, you could come in and give me a number for the voltage that appears across either resistance. And you know, we like to work with specific numbers sometimes because those are real-life problems that we might solve. And when you actually apply your engineering to a real situation, yeah, you're going to solve that specific problem. But when we do our analysis and want to gain intuition about circuits, something that's incredibly common is to take a much more abstract or mathematical approach. So we like to solve problems in the general case. We like to arrive at symbolic expressions that describe a circuit and that are always true regardless of what the specific source voltage is or what the specific source current is, or it doesn't even have to be a function of a source. Say you just want some quantity somewhere in a circuit as a function of some other quantity somewhere else in the circuit. Well, you could totally do that, and it's much more useful to have a symbolic expression because it's a general case answer that's always true. And so I guess one way to think of a voltage divider is a symbolic expression that describes the relationship between one or more, or two or more voltages in a circuit, let's say. Usually it's, in this most basic case, we're going to find a way to relate a voltage across one of these resistances to the source voltage. So what I'm going to set out to do is derive an expression for, we're going to say for V2 as a function of the source. So what that will mean is once I've arrived at the final answer, I'll have an equation that for any given voltage V that you give me, I can immediately tell you what V2 is. So how do we begin? Well, the first thing is we want to know this voltage V2, right? Well, assuming that we know this resistance R, right? These are given resistances, R1 and R2. Then in theory, all we should need to calculate V2 is the current flowing through it. And that's pretty easy because I'm telling you I have a voltage source here and we have two resistors in series, so it's relatively straightforward to figure out what the current is. So clearly the total resistance seen by this source is the series summation R1 plus R2. So I know by Ohm's law that the total current flowing through the circuit, I, equals the ratio of the source voltage to the total equivalent series resistance, which is R1 plus R2. Okay, great, so that's the total current flowing through. But now, also using Ohm's law, it's relatively straightforward to see what V2 will be. So Ohm's law tells us that V2 equals I, or the current flowing through that resistance, times R2. But we have an expression for this current already. So if I plug in this current expression into my formula for V2, well then we'll have that V2 equals V times R2 over R1 plus R2. And that, my friends, is the voltage division principle. I have a solution for the voltage V2 as a function of the source V. Interestingly, there's this extra business here, this ratio of resistances in our circuit. But this is fine, so this is just a constant in theory, right? We're just using resistors. These are real materials, and we're going to assume for a moment they don't change resistance as a function of any other environmental variable. So these are just constant numbers. So this is just a unitless constant. It's a ratio of resistances. And then this is a source voltage that I could give you any number, and then it just scales by this constant to give you V2. Now there's a lot conceptually going on here that I think is very interesting. So the first thing to notice is that clearly this constant ratio is always a number less than 1. Always. I mean, it must be. The denominator here is always larger than the numerator. You're just taking the numerator and adding something else to it, R1. And therefore, the numerator is always less than the denominator. So this ratio is always less than 1. And what that tells us is that V2 is always less than V. But of course, we know that. We know that voltage drops across these passive elements as current flows through them. And intuitively, V2 has to be less than V because some of that voltage V is being eaten up at V1. So KVL tells us that this total voltage V is broken up into voltages V1 and V2. So we know that already. This intuitively we know that the sum of the voltages in this loop, or rather the sum of the steps up equals the sum of the steps down. So we know that all of the energy in this source voltage is split between the two resistances. Some of it goes to V1 and some of it goes to V2. So V2 must be less than V because some of that voltage is eaten up at another resistance. And if you hadn't also noticed, we could have written this analogously as a function V1, or rather a formula for V1 as a function of the source voltage. And if you follow an analogous path or an analogous a sequence of steps here, you can also see how the voltage V1 is a very similar expression, with the exception of the numerator being R1 over R1 plus R2. So each of these voltages eats up a certain percentage or ratio of the total source voltage V. And this is what we already know from Kirchhoff's voltage law, aka the conservation of energy. And we can prove this to ourselves, whereas if we write this solution out, so if we populate in our equivalent expressions for V1 and V2 into this KCL, we arrive at V times R2 over R1 plus R2 plus V times R1 over R1 plus R2. And it's pretty easy to see that if you factor out the V from each side, you'll be left with a common denominator here of R1 plus R2, and the numerator will also be R1 plus R2. So I guess what you're left with is V times R1 plus R2 over R1 plus R2. Well, this is just 1, and so clearly we have that V equals V. And yeah, nothing exciting there, nothing special. We've just verified that this is a true expression, which of course we already knew. It's just Kirchhoff's voltage law. So that should maybe help you convince yourself what's going on here. I guess another intuitive discussion we can have quickly is that, you know, what happens depending on the sizes of these resistances R1 and R2. If you look at V1 for a moment, this ratio R1 over R1 plus R2 is some number less than 1 for any real positive resistances R1 and R2. But what happens is, as R1 gets really, really big, as R1 gets much, much, much bigger than R2, say as R1 gets so large, so as R1 approaches infinity, such that no matter what R2 is, it's so small compared to R1, this ratio gets really close to just R1 over R1. Because if the denominator is a very, very large number plus a very, very small number, it's basically just the large number. And the top is also just the large number. So the bigger and bigger and bigger that R1 gets, the closer this ratio gets to 1, assuming R2 stays constant. And so what you would see in that case is if you had one resistor that was much, much, much larger than the other, it would eat up almost all the voltage. In the opposite case, R1 approached 0, relative to, well, not even relative to R2. If R1 just approaches 0, regardless, you would see how this ratio would just go to 0, and so would the voltage V1. So of course, as R1 goes to 0, if it was 0 ohms, this would be a short circuit, and we know that that an ideal conductor has, or a short has, no voltage across it, so V1 would also approach 0. So why am I belaboring this point so much? It must feel like I'm beating a dead horse at this point. Well, I definitely am, and if this is your introduction to electrical engineering or the concept of a voltage division, it may seem silly, but it's important to realize and just remember this, that every circuit you ever work with, whether it's by design or just a consequence of the system, will contain voltage dividers, quote unquote, or voltage division. So many times we will design circuits that function as voltage dividers, but it just so happens that as a consequence of designing circuits, voltage dividers appear everywhere. It's such a fundamental concept because, in fact, literally any two series resistors form a voltage division. And you can have voltage division, really all it takes is two impedances that share a node. And so you'll see this absolutely everywhere. And these don't have to be resistors either. There's more complicated circuit elements that we'll put in this situation and analyze. But it's just fine to talk about resistors for now. And so point being, this will be something that you do in your sleep. You won't need to write derivations for this. This becomes very intuitive. When you look at the circuit, you know that what happens when these resistors change sizes. You know what happens to the voltages and how it all relates to this current. And this will be like the back of your hand. You will eat and sleep voltage division. I guess with that, maybe this video is getting a little bit longer than I wanted, so I'll go ahead and cut it here. And I think in the next one, I'll talk about current division, which is a very similar dual concept. It'll be a very similar video to this. And then after current division, I think we're going to get into something much more complicated, but also exciting. So let's get ready for that. Anyway, I hope that you enjoyed watching this. I hope it was helpful. Let me know if there's anything I can do to improve these videos in format or content. If you have any questions or need help with anything, please let me know. And again, thanks for watching and have a great day.